Hello, my name is Jose González and I'm going to present the work entitled An Educational Tool for Analyzing and Synthesizing Linear Array Configurations. All the authors of the papers are members of the University of A Coruña, Spain. This is the index of the presentation. First, I will introduce the motivation, next the material and the methods and a bit of theory. After that, the MATLAB-based tool will be shown, as well as some examples using such tool. To end up, some conclusions will be discussed. The main goal of the tool is to help students understand theoretical concepts. There are different types of students. On the one hand, some of the students manage their own methods to gain knowledge. On the other hand, a software tool can improve the motivation of less active users. On his behalf, the professor has a key role, which is to guide, to motivate, and to explain the connection between the theory and the practical results. Finally, the tool helps to apply the theory and observe the results. The tool presented in this work makes it possible to set different antenna-conformal arrays. The location and orientation of the elements, together with the electrical configuration, are specified in order to generate radiation diagrams. The main objective of the work is to provide a tool to the students. However, it's also possible to check the signs in real systems. MATLAB was employed because of the strong orientation to matrix operation. The position of the elements is given by a global coordinate system. Nevertheless, to specify the orientation, a local coordinate system for each of the elements is employed. To evaluate the radiation, we consider points far away from the antenna rays. The direction vectors r and rm are parallel due to that. In such points, the radiation field is calculated as the combination of the fields resulting from each of the elements of the ray. Note from the equation that the magnitude and the phase of the current supplied to the array elements has an impact in the radiation field. We have employed the tool in degree and master courses for computer science and telecommunication students, obtaining good results. The tool is distributed for free under GPL license. This is the main screen of the tool. On the left side, we see the array configuration options. The oriented cones in the upper left figure show the magnitude of the electrical excitation, and the corresponding circles represent the phase. The lower figures show the radiation pattern on 3D and intersections with a cone or a plane in 2D, respectively. The controls allows us to change the angles of the planes and cones, adjust the minimum radiation level, or select the number of points to show. In this panel, we can set the geometric deployment of the elements and use different excitation profiles. Moreover, it's also possible to determine the type of the element. There are two options for the antenna deployments, uniformly and randomly spaced. From the position of the elements, we employ lambda units. When choosing the tapered excitations, a continuous function with normalized values is used for the amplitude distribution. To design the excitation of the elements, we can choose the specific functions such as uniform, cosine, triangular, or Gaussian shape for the arrived amplitudes. It is also possible to use synthesized functions as Chebyshev, Taylor, and WL. It must be noticed that Chebyshev, Taylor, and WL are procedures designed for uniformly spaced elements, and not for randomly spatial distributions. Particularly, the current used in such synthesized functions follow the expressions in the current slide. For further details, see the paper. The last option to set the antenna configuration is to choose between different types of elements, that is, dipole, path, or isotropic. The last option to set the antenna configuration is to choose between different types of elements, that is, dipole, patch, or isotropic. In this slide, we can see an example of a linear distribution of the array. The patches have uniform magnitudes and are randomly separated. The directivity of the generated field can be appreciated in the 3D radiation pattern and in the 2D diagram, which is a slide of the 3D one. In the second example, the dipoles of the linear array are equally spaced and the amplitude is triangular. We can see the radiation pattern in both 3D and a CAD. The third example shows equally spaced isotropic elements, whose excitation is given by the Taylor distribution. To end up with the samples, we show equally spaced isotropic elements with a WL amplitude distribution. To conclude, we would like to remark certain points. The MATLAB tool presented in this work enables students to set different configurations for the linear antenna arrays, both spatially and elliptically, and observe the radiation pattern. The tool is also useful to check real-life designs. In our experience, during last years, students get better understanding of the theoretical concepts when they can simulate them through computer experiments. Moreover, graphic interface is very intuitive for students used to computers. Finally, we are working on a new MATLAB independent version of the tool. Thank you very much for your attention. Do not hesitate to send us any questions.